So before, when we were talking about chemical bonds, remember when we were talking about things like covalent bonds, which are sharing of electrons? Well, electrons would be attracted from one atom to the nucleus of another, and we'd be able to form chemical bonds where electrons were shared. Yeah, sure, okay. And then we talked about how electrons then, if the electronegativity difference between the two elements that were reacting is significant, significantly large enough, then that means that electrons could be transferred from one chemical to another. And you know, here's the thing. If we can intercept that flow of electrons, moving from a thing that wants to give away electrons to something that wants to take them, oh man, do you know that's harnessing energy. And that's electrical energy, turning chemical potential energy into electrical energy for all kinds of uses, like when we have little dry cells or batteries that we have. That's all this unit of study and what it's all about. And it's either called electrochemistry, you can call it that, reduction oxidation chemistry, and we'll talk about those and define those terms in just a second. And it's really about intercepting electron flow and utilizing that electrical energy for a purpose, right? So now, in the unit of study that we've done before, like before chemical bonding even, like balancing equations and talking about solutions, if you were to write an equation about how, say, zinc metal is put into copper 2 nitrate solution, which would then form zinc nitrate plus copper metal, you could write a balanced non-ionic equation for that. And then if you're asked to write the net ionic equation for it, then it would look like this. Now, don't look at that top part yet, but here's a piece of zinc metal, and it reacts with copper 2 ions in solution, and what do you get? You get Zn2 positive plus Cu solid. That's a balanced net ionic equation. But what's really happening there? And I alluded to it before, but now we really get into studying this. What's happening is that the zinc metal is turning into zinc ions because it's going from Zn, with no charge of course, to a 2 positive, so it's not, we don't mess with the protons in the nucleus, right? We're talking about electron exchange. And the zinc is losing electrons. 2 electrons it wants to lose. To who? Well, copper ion in solution is saying, hey, I'll gain those 2 electrons and I'll form copper metal. And that forms what we call a spontaneous reaction in solution, where right away you get an exchange of electrons between those 2 chemical species, and that's called a reduction oxidation reaction. Now, here's why. Because what's really happening is, well, there's like 2 things happening, right? And we can call them, instead of having a net reaction here, well, not just instead of, but this is a result of 2 different things happening that we could call 2 different half reactions. So what are those half reactions that are occurring? Well, zinc solid is turning into zinc ion, and it's losing 2 electrons. And when we say lose electrons, that means electrons are written on the product side because they're being produced, they're being lost. Okay, so zinc is turning into Zn2 positive, losing 2 electrons, and what we call that, when the electrons are written on the right-hand side, electrons are being lost in a half reaction, we call that oxidation. You're being oxidized. And generally, well, that really comes from the fact that oxygen itself is something that really likes to take away electrons from a lot of chemicals on this planet. So if you've been oxidized, you've been beaten up by oxygen and had your electrons removed. Okay, well, not every reaction has to involve oxygen, but we still call it oxidized when you get your electrons taken away from you. And who's taking the electrons? And by the way, you don't necessarily want to lose those electrons. Zinc metal is perfectly fine just being zinc metal, sitting out on the table, except it does react with oxygen in the air because it gets a little oxidized. But the point is, you can take that zinc metal, and copper ions are saying, hey, if you put me in contact with that zinc, I will take those electrons. And so copper ions will take those electrons from the zinc, who will then lose them. And because the charge of the copper is going from 2 positive to 0, it's going lower. When the charge goes lower, we call that reduction. So here's the deal. An oxidation-reduction reaction occurs when you have a chemical species that wants to lose electrons to something that's going to take those electrons and undergo reduction. You can't have 2 of these half reactions coming together to make a whole reaction where the electrons are both written on the right-hand side, because that would both be oxidation, and that doesn't make sense. Or you wouldn't have these two electrons here on the left-hand side added to this equation too, because that would be both of them undergoing reduction. The reactions are not red-red and they're not ox-ox. Here's what they are. They're redox reactions. Redox reactions. Something is losing, something is gaining. Now, and to further these definitions, and you have to have these terms under control, you really do, honestly. Here's what some more terms that are involved here. This is oxidation, this is reduction. Now again, what does this reaction want this one to do? It wants it to lose electrons. This copper ion right here is the agent by which this becomes oxidized. And so, we call the copper 2 ions here in this setup the strongest, or just the oxidizing agent. Sometimes we write SOA for the strongest oxidizing agent in a group of chemicals. Well, so an oxidizing agent itself undergoes reduction. And reduction is gaining electrons. I know that sounds weird. Reduction is gaining, but chemistry is weird, right? Okay, so there you go. But the oxidizing agent undergoes reduction, and that means it's gaining electrons. Electrons are written on the left. What does that mean then? That one is going to be called the reducing agent. A bunch of chemicals put together, we say, ooh, that one's the one that loses the electrons. That's the strong reducing agent. So, in this little reaction right here, the zinc metal is undergoing oxidation. It is the reducing agent. It's losing electrons, which means the electrons are written on the right-hand side of the half reaction. Now, and of course the copper is the oxidizing agent, which means it's gaining electrons, which means it's undergoing reduction. Electrons are written on the left-hand side. How do you know if a reaction takes place at all when you put chemicals together? Because you know what? When you put zinc into copper ions, like I said before, and I use this word, that's a spontaneous reaction. This reaction is spontaneous. But that actually means, and it doesn't just infer or imply, it means this, that the reverse reaction here is non-spontaneous. If you put a piece of copper metal into zinc ion solution, nothing happens. This forward reaction likes to happen, but not the reverse reaction. So the reverse reaction of a spontaneous reaction is always one that won't take place under normal circumstances, and that's called non-spontaneous. How do you know? You kind of need to have some information. Maybe a chart that explains everything too. So let's get into answering another one of these types of questions as to, well, let's put some reactions together and how you would do that with some information.